We're going to begin Unit 6 over stoichiometry, and we'll define stoichiometry in just a little bit, but we are going to be doing a lot of calculations, so you're going to need periodic table so that you can do the molar masses and those types of things again. So let's get started. We will be doing some practice problems today with reviewing on how to get liters and grams and things again, since it's been a while. So first of all, chemistry is a lot like a recipe. A balanced chemical equation provides the same type of quantitative or number information that a recipe does. I know that it's a little blurry, but I'm assuming that at this point all of you have seen some type of a recipe. And in that recipe it tells us how much, and it gives us a unit like cups or tablespoons or whatever it might be, so that we could properly make our end product, in this case cookies. Well, in chemistry we need that same type of information. We need a balanced equation so that we can create whatever type of product that we're looking for. So this is why balancing equations is important. We've also looked at predicting the products so that we know what type of product would be made in different chemical reactions. And now we're going to be looking at calculating how much of the reactant or how much of the product do we need if we have a certain amount to begin with. So stoichiometry, these are calculations that you are doing in these chemical reactions. So we're looking for quantities. How much mass are we going to produce of our product? How many liters of gas can we create when we add these two reactants together? Whatever it might be, we're going to be looking at quantities, so it's a lot of numbers. We're definitely going to be doing a lot of calculations again, so calculators are a must. Chemists can track your reactants and the products, and we can use 4 different methods on tracking that. We could track it by the mass, the grams of each reactant or product. We can look at the moles. We could look at the liters, or we could look at whatever the representative particle is, like molecules or formula units or atoms if we're looking at an individual element. And I just threw this equation together. I know that there's other things that go into creating cookies, but I wanted it to look like a chemical equation that we've maybe done in class. So we have a balanced equation because we have how much of each item we need, and if we were to add the correct amount of each item, we should be able to produce 2 dozen cookies. Now if we only added 2 eggs instead of 4, but we kept all the other ingredients the same, then our cookies are probably going to taste funny and we might not be able to get 2 dozen of them. So you have to have a balanced chemical equation. And I want to know, my son needs 5 dozen cookies, not 2 dozen. He needs 5 dozen cookies for a class project. How many eggs do I need to make 5 dozen cookies? Well, we can use some conversion factors. Okay? We know that we need 4 eggs for 2 dozen cookies, or you can always reverse your conversion factors, flip them, mean the same thing. For 2 dozen cookies we need 4 eggs. And you are going to be doing the conversions, canceling of units, and so if we were to set this up like we do in chemistry so that units cancel, we would start with what we were given in the problem, that we want to make 5 dozen cookies. So we're going to start with 5 dozen cookies. We want the cookies, the dozen cookies, to go away, so we're putting that on the bottom, so our units will cancel. And instead of cookies, we want to know how many eggs, and so we're going to be using this conversion factor because that's the one that has the dozen cookies on the bottom, and that's the way we needed to set it up to get cookies to cancel. So we're ending with eggs, and you probably have already done the math in your head, because this is something that if you've done any type of cooking you may have had to adjust a recipe, but you would need 10 eggs. Okay, 5 dozen times 4 eggs, but then divide it by 2, so 10 eggs total is how many I would need for 5 dozen cookies. Well, we're going to be doing that only with chemistry type units. So let's take a look at how we can interpret a chemical equation. First of all, you have to have a balanced equation. If it's not balanced, that's the first job. Always make sure that you have a balanced chemical equation. And once it's balanced, then we can determine the different amounts of, in this case, nitrogen and hydrogen and ammonia that we need. We can determine the amount of atoms of each one, molecules, moles, the mass, and the volume. So let's take a look at the number of atoms. We know that we have 2 atoms of nitrogen because it's N2. We have 6 atoms total of hydrogen, 3 times 2 in our balanced equation. And then that produces 8 atoms total. Now those 8 atoms have been recombined so that nitrogen and hydrogen are now bonded together, but we have a total of 8 atoms. We have 2 from nitrogen, and 2 times 3 is 6 for hydrogen, so that's still a total of 8 atoms. And atoms are something that are always conserved 100% of the time. So if you look at your reactants, we have a total of 8 atoms between nitrogen and hydrogen, and on the product side we also have the 8. Now we can also look at the number of molecules, and in this case they're all covalent, either elements bonded to themselves or a compound, but they're all molecules since they're all nonmetals. So we have 1 molecule of nitrogen, and that's because there's just a 1 here in front of N2, but it takes 3 molecules of hydrogen, and those 2 items together, when we combine 1 molecule of nitrogen, 3 molecules of hydrogen, we can get 2 molecules of the ammonia. So those balanced equations, those coefficients, are incredibly important. If we don't start with them balanced, then we can't interpret any of these items that we're interpreting. We can't do that. Now, we know that molecules are really small. We can't even see a molecule of nitrogen. So we're going to be using Avogadro's number, and we're going to be converting those into the larger amount, because if you had to do a recipe and you had to combine things together that you can't even see, that'd be incredibly difficult. So we will be converting these into Avogadro's number in most of our cases. Now we can also interpret this for moles. So I know with the flipping of the slide the equation isn't there anymore, but we're still using the N2 plus 3H2 produces the 2NH3. We're still doing that. But in moles, the coefficient, the number out in front, tells us the number of moles of each reactant that we need. And this is going to be the most important information given to us in our balanced equation. I can't stress that enough, how important this is. You have to have a balanced equation, because this mole to mole ratio that we're going to be making eventually is what is going to allow us to be able to take a reactant and be able to determine how much product we can form. We have to have balanced equations, and we're going to be using moles a lot. The number of moles of our reactant don't have to equal the number of moles of our product. That's one of those items that are not conserved. That is definitely going to come up on a test. Conserved. If you look back at the original problem, we had N2 plus 3H2, and that only gave us 2NH3. This says that we only have 1 mole of N2, 3 moles of H2, 2 moles of NH3. Well, if you add up all the reactant side, that's a total of 4 moles. If you add up the product side, it's a total of 2 moles. So moles are something that are not conserved in a balanced equation. Now, mass, the balanced equation always obeys the law of conservation of mass. We know this from our last unit. So this is an always obeys the law of conservation of mass. If it does not, then you do not have a balanced equation. And so you need to go back and do that. Make sure it is balanced. In this case, if we take a look at the fact that 1 mole of N2 from our original balanced chemical equation, we know that N2 would be 2 times the molar mass of nitrogen, so that's 14.0, so there's our 28 grams of nitrogen. H2, and there's 3 moles of that, so H2 would be 2.0, but we have 3 moles of it, so that we have a total of 6.0 grams. and then 2 moles of NH3. We would have to look up N and our 3 H's. N's 14, hydrogen 1 each, so you're at 17 grams. There's 2 moles of that, so that's where we're getting the 34.0 grams total. 28 plus the 6.0 is going to give you 34 grams. So in this case, mass, and in all cases, reactants equal the products. And then lastly, we can also look at volume. So this is only if we're under our standard temperature and pressure, then we can also know the volume of each of our gases. So 1 mole of N2, we know 1 mole is equal to 22.4 liters. So for nitrogen here, we only have 22.4 liters. We have 3 moles of the hydrogen. So 3 moles would be 22.4 times 3, so we have 67.2. And then we have the 44.8 liters of ammonia because 2 times 22.4. And so that's how we could interpret it. One chemical equation can be interpreted in all of those various ways. As far as the mass and atoms are always 100% of the time, every time, always, every time conserved. Okay, I can't express that enough. If you did not know that on the last test, definitely going to be on this one again. The other items don't have to be conserved. There are some times where it works out that they are, but that's just going to be a coincidence. It's not going to be every equation that it works like that. So molecules are not always conserved. The formula units, moles, volume, those things are not going to be conserved in every single case. Now we're going to go through a practice problem where everything's already kind of set up. So I'm going to be going through this with you, and you're going to be jotting some things down. First of all, I want you to notice that we have a balanced chemical equation. That has to happen first before you can do any interpreting of the equation. Make sure it's balanced. Now we want to interpret this based off of representative particles, moles, and mass. So if you look back at your notes, those were 3 of the items, 3 ways that we can interpret them. So the representative particle is going to be molecules, because each of these, H2S, is a it's 2 nonmetals. Oxygen's nonmetal, sulfur and oxygen nonmetals, H and O nonmetals. So we're going to be using molecules for our representative particle. So we have 2 molecules of the hydrosulfuric acid, H2S, 3 molecules of oxygen. We have 2 molecules of the sulfur dioxide, and 2 molecules of water. So we're just taking our balanced equation, our coefficients, and that is representing, in this case, molecules. But we can also use the coefficients for moles as well. So we have 2 moles of the H2S, 3 moles of the O2, 2 moles of SO2, and 2 moles of H2O. So we have taken care of the representative particles and the moles. Those have been interpreted by writing out these equations here. And now we want to look at mass. Now this equation doesn't tell us the mass. This is something that we're going to have to calculate. And so I have all of this up here for right now, but I want to make sure that we just take a look at it. Notice our plus. So we're doing 4 separate problems right here. We have 2 moles of H2S, and we know that if we want to convert something to grams, we have to put moles on the bottom, grams on the top of our division bar. And you have to do the molar mass of this. So H2S has a molar mass of 34.1 when you calculate everything from your periodic table. And we have 3 moles of O2, and we know for every 1 mole of O2 we get 32 grams, 16 plus 16, since there's 2 oxygens. 2 moles of SO2, well, we have 1 mole is equal to 64.1 grams, and again we would have to take 1 sulfur, adding it with the 2 oxygens. And for water, 2 moles of H2O, we have 18.0 grams for our molar mass of water. Now when you calculate all of that out, just by doing the multiplication and getting your final answer, 68.2 grams of H2S, 96.0 grams of oxygen, 128.2 grams of sulfur dioxide, 36.0 grams of water, and you could add up your reactants and your products, and occasionally it would be good to check your work and just make sure that you end up getting the same amount of reactants as products, because if you don't, you've done something wrong. You really need to make sure that those are the same. Alright, so now let's take a look at a new practice problem. First of all, you always want to start with a balanced equation. And so in this one, we are going to start off with carbon. We want to balance that with a 2. We want to balance our hydrogen, and they already are balanced. 2 H's over here, and on our product side also has 2 H's. And now we need to balance oxygen. By the way, you should know what type of chemical reaction this is, since we are adding oxygen and we're getting carbon dioxide and water. Hopefully you recognize that this was a combustion reaction. But for our oxygen, this is one of the tricky ones. 2 times 2 gives you 4 oxygens. You only have the 1 here. So that means that we have kind of an odd even. There's nothing that we can put in front of O2 that would give us 5, except for a decimal, which we don't want decimals. So we are going to start over here. And the first thing I'm going to do, so that I don't get that problem again, is I'm going to go through and I'm going to multiply. I'm going to start off with 2 moles of this item. So now I have, where originally I had a 2 CO2, I'm multiplying that by 2 as well. So I have 4. And now I have my hydrogens. I have a total of 4, so I need to put a 2 here. And now my oxygens will be able to balance. I have a total of 10 oxygens on my product side, and so if I put a 5 here, I'm going to have a balanced equation. So you always start with a balanced equation, and now we can get into all of the writing. Okay, for this particular one, we've done moles and we've done mass already on the previous example. So when you're interpreting this for moles, you have to take the coefficient. We would say that we have 2 moles of the C2H2, and we're going to add that to 5 moles of O2. Just like if it was a equation you were doing in your kitchen and trying to, make a batch of cookies. Alright, we have 4 moles of CO2 and 2 moles of water, H2O. So to interpret it for moles, those coefficients are telling you how many moles of each reactant and product you have. So moles is done. Now mass is the one that's going to take a little bit more space. So I know I have 2 moles, and might get tricky to write all of this in here, but we need to make sure that we're practicing that. And I want to convert moles to grams, and so I'm going to do that with a molar mass, and so that would be 26.0. And I'm going to add to that my 5 moles of oxygen, and I have to convert moles of oxygen into grams of oxygen. And my molar mass of oxygen is 32.0. Now on my product side, I had 4 moles of CO2, and for every 1 mole of CO2, I get 44.0 grams. Again, you are going to need to get out your periodic table, and you could always double check these, but just to make sure that I have the right molar mass. And for 2 moles of water, we want to convert 1 mole of water, and that's 18.0 grams. Alright, so that's just setting up all of your molar mass problems. All we're doing is converting moles to grams, and we're using the molar mass from our periodic table for each of these compounds. 2 times 26 gives me 52.0. Make sure you're using significant digits. C2H2. 5 times 32.0 gives me 160 point. I'm only allowed 3 significant digits, so I want to keep that decimal there. That's grams of oxygen. My 4 times 44 gives me 176 grams of CO2. And my 2 moles times 18 grams is going to give me 36.0 grams of water. Now if you added all these up, just to double check your work, you're going to end up with 212 and 212. So it's always good that mass should always come out being equal on the reactants and the product side. Now let's do volume. Okay, we didn't do volume on the previous screen, but to set this one up, it's going to look similar to what we've already done. So we have 2 moles of the C2H2, And we know that for every 1 mole, because we want moles to cancel, we get 22.4 liters. And so for every single one of these, you are taking the amount of moles of O2 here, and we're converting 1 mole into 22.4 liters. So we're doing that for every single one of these. They were all in gas form if you look back up at the original equation. So our 4 moles of CO2, again, the conversion is 1 mole is 22.4 liters. And lastly, our 2 moles of water, which would be steam in this case since it's in gas form. 1 mole is 22.4 liters. Alright, and so if we wanted to get a grand total number of moles, we have 44.8 liters, sorry, not moles, of our C2H2. We have a total of 112 liters of oxygen. Those are our reactants. On our product side, we end up with 89.6 liters of CO2 and 2 times 22.4, 44.8 liters of H2O. Alright, so that would be interpreting it for moles and mass and for volume, assuming that we were at STP.